Today in this video, we are going to study about the search engines. By the end of this video, you will be able to know two things. First is about how Twitter search engine work. Secondly, you will also understand how Elasticsearch is working. So these are the two things that you will know by the end of this video. So without wasting any time, let's get started. So first of all, we are going to discuss about what is a search engine. So basically, search engine can be in any platform. We are going to discuss in respect of Twitter, but think of it that if you are using Instagram or any other platform where the user will come, type a query, and there we are going to have a bunch of data, and out of that bunch of data we are going to return some sort of a response. I will give you one simple example. Let's say in our database of Twitter we are going to have a lot of tweets. So let's say tweet 1 is saying I love Java, tweet 2 is saying something, and tweet 3 is saying something. Now the user will come, it will do a query, let's say Java. When the user will do a query, so in that scenario we are going to return tweet 1 and tweet 2 to the user because user is searching about the Java. This is how a simple search service is going to work. Now we are going to discuss how we can make this service. This is the main idea of this video. Now let's discuss about the functional and the non-functional requirement of the search engine that we are going to discuss. So first functional requirement says that we have to search the tweet by the text. Basically we have to search the post if we are talking in terms of Instagram. Second point of functional requirement is return relevant results. Think of it, if I am searching the word Java, and now what is going to happen, let's say there are going to be a million posts related to Java. In that case, are we going to return all the million posts to the front end, or we are going to return the top 20 Java posts? And how we are going to figure out that 20 Java posts? This is the point of discussion. Now we should also support some filtering. Basically, not only Java, let's say the latest post, okay, and there can be other posts that, let's say if we are searching for any region, then the post from that particular region. Let's say let's say we can also have a time filter that the post should be after, let's say 10 p.m. or after that date. Then we can put some filters like that. There should be a pagination, that will be a discussion of the search service. Let's say if we get 100 posts, we should return only 20 posts, the top 20 posts, and it should be very fast so that we can get the post from the second page as well. Okay, so these are the functional requirements that we should support. Now we are going to talk about the non-functional requirements. In the non-functional requirement, it should be supporting low latency. It should be very fast, highly available. It should not go down. It should give some response to the user. Scalable, it should be scalable, supporting, let's say, millions of tweets, not even million, billions of tweets. Freshness, this is an important point. That's why I wrote an example here. Think of it, if a user posted something at 10:01, now that post should be available for searching at 10:01 itself. This is the requirement. Basically, if I posted something, and let's say if I posted some random words, let's say XYZ or something, okay, and if I posted something, then if I search that particular keyword, I should get a response at the same time. If I posted something at 10:01, it should be available for searching at 10:01. This is the requirement of the system. Relevance. Okay, the relevance point I have already discussed with you. If I search iPhone, then what are the relevant results for the iPhone? This is the main point. Let's say for the iPhone keyword, we got millions of posts, and out of million of posts, what are the relevant results for this user? Let's say if I'm in India right now, then if I search iPhone, then maybe there is a post going on, iPhone charges has increased in India and iPhone charges has increased in America. Which post will come to me first? Basically the Indian one or the American one? This is the point of discussion. So the post should be relevant. So these are the non-functional requirements. Now we are going to talk about the approaches, how we are going to make this search system. So there are going to be many different ways, and by the end of this video we are going to do a discussion about how Twitter made it, how Elasticsearch work, and all this. So first of all, we are going to start with the basics. We are going to do the approach one, MySQL plus like. Okay, it's a simple approach. What is going to happen right now, we are going to store the tweets into a MySQL database. There's going to be ID and the text, and simply I love Java, learning Python, and Java is fast. Simply we stored everything into the MySQL database, and after that we can just write this query. Select star from tweet where text like Java, okay, %Java %. Now what is going to happen? It is very simple. No new system is required in that. Okay, let's say there is a single database. We are going to write this query and it is going to give the result. fine for small amount of data, and it works pretty well for small amount of data. And but of course it is going to fail for Twitter because Twitter has billions of document, data is going to be sharded. Secondly, it is not going to support the ranking that we have discussed. Basically, we don't know which is the actual amount of data, which is the actual result that we have to return to the user. This is the things that this approach cannot solve. For a large amount of data, we may scan a huge number of rows. Okay, so let's say billions of documents, we are scanning a lot of documents in that. But as in my video, I always say these approaches are not bad. Maybe these approaches will work very well when you are making the small systems. Okay, this approach is not going to work for Twitter. This is the only thing. There is no right approach and no wrong approach in system design. Please remember this point. Now we are going to talk about the normal database indexing. That is the approach 2. So what we are going to do in this approach 1, we are using a simple table, and now in the approach 2, what we are going to do, we are going to make an index on this text column. So let's say if I put an index on this text column, now what is going to happen? Basically, if we put an index on this text column, then the search is going to be fast. But in MySQL or in any database, in the indexing concept, we usually use B trees and B plus tree. B trees and B plus tree work very well with numbers. Okay, it works also good with strings, but the thing is that it is going to work good with string when the data is sorted, plus that if we are searching at the first index. Basically, if the text starts with Java, it works really great because in B trees and B plus tree, the data is going to be sorted, and then you can like implement a binary search over it. Then it is going to be fast. Everything is going to be perfect. But right now, the requirement says that Java word can exist anywhere in the text. This is the problem. So that's why B trees and B plus tree indexing is also not going to work. Of course, it is going to give you the better results without indexing. Indexing can improve the approach 1, but it is not the final solution. So pros and cons, database already supports it. It is very easy to implement. Indexing exists in database. Very fast for exact value, ranges and the prefixes that I have discussed. No separate infrastructure. There is no separate infrastructure needed for the searching. We can just do it in the database. Cons is not good for arbitrary words inside large text. We cannot figure out the exact word, let's say Java, inside the text. It is going to be very difficult for the P trees and the B plus trees. Doesn't naturally solve a token based search. Okay, and search ranking is very difficult because again it is not solving the ranking problem that is still unsolved. So we discussed about the approach 2. Now let's move to the approach 3, that is inverted index and the full text search index. Many of the databases also supported full text search index, that we can say inverted index. So what is going to happen now? Think of it, there is a tweet. This is the data that we are going to store into our database as it is. After that, what is going to happen? We are going to give it a full text search index, basically inverted index. Now, before storing it into our inverted index, I tokenize it, I remove the stop words. Now the tweet 1 says love and Java, tweet 2 says Java and fast, tweet 3 say love and Python. I remove I, is and I. Basically these are the stop words. They are not making that much sense for the keywords. Basically we just want keywords in our inverted index. Now in our inverted index, what we are going to do, we are going to keep the data like this, basically Java and in front of tweets, basically list of tweets. Love, tweet 1 and tweet 3, fast, tweet 2 and Python, tweet 3. So this is like this. This is the concept of inverted index that is also supported by the database. This approach is very good actually. The thing is, and this approach is going to give you the final solution of the searching. This is now there is a small problem in this inverted index concept, that in scale of Twitter, there are going to be millions of tweets that we are going to get. If we are going to get millions of tweets, we have to update this list. Basically, in front of Java, there is going to be update of list. In iPhone, there is going to be list, news list. Now, in this list, we have to do a lot of things. First of all, this list is going to be updated again and again. That is the first problem. Second problem is the ranking issue is not solved till now. So these are the main problems in this list. But I have wrote all the things down for you. What are the pros and cons of this approach? So it is of course better than easy to add an existing application, Good for smaller medium search system, of course. This inverted index really works well for smaller systems. Like if you're not making Twitter, you can simply go with the inverted index and you can simply make the system work. No completely separate search platform needed. Think of it, till the time we didn't make any separate search index. In all the three approaches, database is easily able to support the searching. We are not thinking of anything separate. We are not making any extra search service or anything. We are just taking help of database anyhow, and it is like we are getting some results. Now we are going to talk about the cons. I wrote two cons for you. So first of all, let's discuss these. So in this cons I mentioned, search is now competing with our main database workload. Okay. So think of it, the request is coming, let's say the write requests are coming, read requests are coming, and the search request is also coming to the same database. This is the problem in this approach because we are using still the same database. Index also exists in the same database. This is the problem. Less flexibility for complex ranking. Okay. Like we didn't implement the ranking till now, but let's say if we come up with some logic, later on we will come up with some logic, but right now there is going to be a problem with the ranking. Scaling search independently becomes harder. If we want to scale the searching, it is very hard. We have to scale the complete database because scaling still, that searching still exists into the same database. Search specific features become harder as requirements grow. Yeah, so these are the problem that we were facing when our index exists in the same database. So let's solve this problem. Now what we are going to do, that we are going to separate our search from the database. This is something that we want to do. So if we separate it, then there are some other problems that we are going to get. So basically, if you make a separate search service, I mean to say, if we are going to have a separate DB for the searching, there is one database for our main data and there is going to be another database for inverted index. So basically, we are storing the same data twice, for one for the indexing and one for our main normal tweets. So the problem is we have to store more infra. We need more infra, of course, duplicate data because tweets are going to be stored into the database and we are storing the same tweet invertedly in the next database for inverted index. Keeping DB and search index synchronized. We have to synchronize the things because the tweet comes at 10:1 and we have to store the same tweet at 10:1 at the search index so that it can be available for searching again. Handling failures is very difficult. New tweet must quickly reach to the search index. This is the cons. Okay, so we have discussed all of them, but this is the right approach. If we improve this cons somehow, then we can lead to the right system. This is something that we are going to do now. Now let's talk about in terms of Twitter. So Twitter has 6 problems, and we know that we discussed these 3 approaches that also have some problems, and we are going to solve all of them one by one. So let's discuss about some Twitter problems now. The problem 1 says the index become huge. As we are going to go with this inverted index approach, the indexes are going to be huge. Basically, if we have one machine and there are millions of tweets coming, the indexes are going to be huge, and again, it is going to create a problem. Secondly, new tweets arrives continuously. So think of it on that same list, basically Java, and in front of that there is a list. Now, again, there is a problem. That problem is that that list is continuously, like someone is writing into that list again and again and again, and we have to read also from that list. So two things are happening. The write load is also so much and the read is also too much. So we have to control it somehow. We have to come up with some solution. Okay, and we have to like figure out the ranking as well. Third problem is search must be real time. If we are going to have a separate database, then we have to update into our normal database and we have to update our searches as well. So this is something that we have to do. Fourth problem is one query may need many machines. Okay, if we are going to think of this, that if we are thinking of problem 1, new indexes, the indexes become huge. So basically we have to shard the query. Basically we have to shard our inverted index databases. Then if we shard the database, in that case, we have to make a query to many machines. Okay, so you have to come up with that approach as well. How we can query multiple machines and get the best answer. Ranking is much harder than matching. Still, we don't know how we are going to rank. We don't know this approach till now. And failures is normal. Basically, let's say if we sharded our inverted indexes table. Basically, if we sharded our inverted indexes database somehow, and then let's say if one of the machine dies, then how we are going to return those particular tweets. Let's say if we have sharded, let's say we have three databases in which let's say tweet 1 and tweet 2 exist in database A, tweet 3 and tweet 4 exist in database B, and tweet 5 and tweet 6 exist in database C. Then in that case, let's say if database B dies, then we are just going to guess 1, 2, 3 and 1, 2, 5 and 6. So these data is going to be lost if our one of the shard dies or one of our DB dies in terms of searching. So this is the problem in our failure. So these are the Twitter problems, and these are the normal problem with the inverted indexes. While we are managing our separate search indexes database. Now we understood all the problems. Now we are going to talk about the solution and how we are going to tackle all these problems one by one. So the solution is Earlybird. It's Twitter custom real-time distributed search engine. Twitter already moved from MySQL to Lucene because the relational approach was becoming difficult to scale. Okay, if we discussed about all these approaches, the relational approach that we have discussed. Okay, but it was not working for Twitter. That's why Twitter is going to make something known as Earlybird. Before I'll show you this Twitter search engine internals, I want you to know that this Twitter can also use Elasticsearch, and Elasticsearch is one of the best distributed system that also worked on Lucene, solve this purpose of searching. But Twitter is not using it, but the architecture is going to be very similar to Elasticsearch. So in later on somehow I'll going to make a video on Elasticsearch as well, but this video is also going to give you an idea how Elasticsearch works. Now let's talk about Twitter search engine internals, how it is working. So first of all, what is going to happen? First of all, we are going to see an approach how we are going to write the data into our search engine. Let's see how Twitter made it. So first of all, user will basically post a tweet. It will go to the tweet service and it is going to store the data into this Manhattan DB. I've told you what is a Manhattan database. I made a separate video on that topic. You can just go to that video and study about the Manhattan. Now it will go to the Kafka. So why we are choosing the Kafka here? Basically, we are sending our data to search ingestion service. Now the thing is, if we are sending the data to the search ingestion service, in Twitter, we have to do a lot of things with our tweet. Basically, we have to send it to analytics service or any other service. So that's why we are putting Kafka here, so that we can send this data to the tweet data to the search ingestion service. And now what the search ingestion service is going to do, search ingestion service is not going to put the raw data that we put into our Manhattan database. It is going to sort the data. Basically, it will tokenize that we have discussed. It will remove some of the data. Secondly, it will detect the language, extract some fields and extract some features from that tweet. These points we'll cover it later, and how these points are also going to help you in ranking. Okay, we'll discuss about them. But this is what search ingestion is doing. It is going to tokenize, detect the language, extract some raw fields, extract some features, figure out that there is a URL or not, there is an image exist or not. We will figure it out, and this is what search ingestion is doing. Now the search ingestion is going to again put all these like modified data into the Kafka. Okay, that is the first Kafka, then that is the second Kafka. After that, this data will reach to Earlybird distributed Lucene index. So now what is going to happen? This is a distributed system that works on the Lucene indexes, and now in this Lucene indexes, what is going to happen? There are going to be distributed systems. So there are going to be multiple shards, shard 1, shard 2 and shard 3, and there are going to be replicas as well of these shards. Basically, if the shard 1 or the replica 1 goes down, there is a replica 2 to still giving the responses. Okay, this system is highly available. Now this is the system. We are going to deep dive into it. And now what is going to happen when the user makes a search query? The user will make a search query. It will go to the search service. There are some things that I mentioned. We are going to discuss them later on. And these requests will go to the shard 1, shard 2 and shard 3. I'm going to discuss about this fan out request also, and it is going to give you the response. So this is the basic system. We are just going to use Earlybird distributed Lucene index that Twitter has built, and that is going to solve all the problems. So now let's deep dive into it, how they have built it. So first of all, we are going to discuss about the search ingestion. What is happening in the search ingestion that I was telling you? So that is the tokenizer. Basically, if the tweet says I love Java, so tokenize will remove this I and normalize it into love and Java. So this is our normal tweet, and now figuring it out, what is the language? Let's say language is English, user ID is 50. Is there any hashtags, URLs, features, basically images and all? So this is something that search ingestion is doing. So I told you in the starting that everything, this whole search concept is working on the inverted indexes. Okay, so basics is simple, that we should know what is the inverted index. And now we are talking about the Lucene, okay, because we are using this word Lucene. So Lucene is a Java search library. Okay, so now this Java search library do the same thing, Java and in front of all the tweet IDs. But the thing is that Twitter modified it a little bit. So what is the modification and how it is improving their performance? So basically the lock-free structure. The lock-free structure means basically when you are writing something, you can make a read call at the same time. So there is no locking at the time. Thirdly is early query termination. That is an important concept that you should know. Think of it, let's say the requirement says that you need 20 records. When you are searching the Java, you make a database call. When you make a database call, it is returning you the 1000 records, and when it is returning the 1000 records, basically it is writing somewhere 1000 records and returning you the 1000 records. Okay, but how much data that you need? You need only 20 data, and then of course you can put a thing, something like limit and offset. But if I say I need 20 records, and if I figure out only 20 records and then I terminate the whole process, that is something that Twitter has achieved. You figure out 20 records and terminate the whole process. You just need 20 records, you get it, and you terminate the whole thing. So this is what Twitter was doing. So that is something that they have achieved with the Lucene. Okay, that is the Java library. They have implemented it and they have modified it, and then they have achieved these two things. And there are other things as well. You can go to Lucene and you can study about them. Now we are going to deep dive into all these shard in this structure. Now I made this whole thing here. So the first problem in our inverted index is that inverted index is becoming very big. So what we did is that we sharded it as well. So this partition 1 or partition 0, you can say shard 0, shard 1, shard 2 and shard 3. So basically we are using simple hash based sharding here, and tweet IDs is going to divide with, let's say, modulo with number of partitions, or let's say number of shards that exist in our Earlybird. So in our case it is 4. So tweet 100 will go here, tweet 104 will go here, and so on and so forth. So the thing is, let's say if a keyword Java comes, so this Java keyword will be existing in different shards. So let's say on shard 0, Java exists in tweet 100. On shard 1, Java exists in tweet 101. On shard 2, it doesn't exist. On shard 3, it exists in 103. This is how our data is going to be stored in our shards. So now we solve the problem of one. Okay, now we have multiple lists exist in multiple shards. We are maintaining multiple Lucene indexes in multiple shards. This is something that we are trying to do. Now, if we make a search query here, basically we are going to send the Java to all the shards, this shard, this shard, and this shard. And when we send this query, Java query, to all the 3 shards, we are going to get the different list, and then we can merge them, and we can send it to the user. That is why I mentioned the fan out request. Whenever the search query is coming, then what we are going to do? We are going to do a fan out request. Instead of requesting to one shard, we are sending the request to multiple shards. Let's say there are 10 shards running. We send a fan out request to 10 shards. These 10 shards is going to return a response. And after that, what is going to happen? We are going to merge those responses, and then we are going to send it to the user. So that's why I mentioned the word merger here. Okay. And now we have also discussed about the fan out request. Okay, we have discussed this as well. We have discussed about the Lucene as well. Now let's move forward. Now I'm going to take you deep dive into this shard. How this shard work, basically how they have actually created this shard. Okay, so this is the more internal that we are going to deep dive now. Now here you will notice what is going to happen. First of all, the first step is the index writer. The index writer is going to do the same thing. Basically, the response that we get from the search ingestion, it is going to put them into our entry, into our, basically into the shard. It is going to store it. Now we have the segment manager. This is the important thing. The segment manager is going to put the records in the segment. Think of it, the first million, 1 to 1 million is going to be stored in the first index. Then segment 2 is going to store the data between 1 million to 2 millions. Segment 3, 2 millions to 3 million, and so on and so forth. But the thing is, the last segment is going to be the always active segment. So new tweets are going to come and they are going to be stored into the active segments. This is the whole point. Now there is going to be a query. So basically, whenever a user will send the search query, it will come, and now what is going to happen? It will go to the searcher, and now searcher will also do a fan out between these segments. Okay, now the searcher is also going to do a fan out between these segments and going to return the same thing. Basically Java between these 1 and 1 million, Java and 1 and 1 million, and it is also going to give you some list, going to merge it and return to the search service. Okay, so there is one fan out on request here, and whenever there is going to be a fan out on request internally that is happening between in this shard. So I have discussed about a 2 fan out of request that is happening. Now we are going to discuss one more thing, how the ranking is solved. For ranking, you should know 2-3 things. Okay, so that I have discussed it here. Static signals, dynamic signals, and the query time. So for the static signal, think of it, a tweet, when someone posted a tweet, it is going to have images, URL, and the languages. That is going to be static. Once a user has posted a tweet, it is going to contain some image, URL, and language. Okay, that is the static data. Okay, it cannot be changed. Secondly, dynamic signals. The dynamic signals means likes, comments, retweets, and replies. That is what changing continuously, and that is how the ranking of a tweet is changed. Okay, and there is going to be time factor as well. Okay, with the latest tweet or the oldest tweet. Let's say that tweet that we have posted, first of all it has, let's say, 100 likes, and later on that post had 10,000 likes. Of course, the ranking of the tweet will goes up. So these are the factors. Retweet is also a factor. How many people have retweeted that post? So these are the factors that we should consider. That are the dynamic signals for the ranking. Third is the query time. Okay, that is a searcher graph that also you should consider. Think of it. Let's say if I follow person B, okay, and that person has posted something about Java, and there is one more person C, okay, that person has also posted something about Java. So when I do a search, so I should get the B's person post first because that person is my friend. So that is something that you should know. That is known as a searcher graph. So basically we follow someone, that person's post should come first, then to the someone that is, let's say, that is some unknown person to me. So that is one more thing that you should know. So these are the 3 parameters that we should consider. There can be more parameters as well, but I am just using these 3 parameters to explain you the concept. Now, what is going to happen? How we are going to implement this ranking as well in this system? So whenever we are going to do the search service, okay, one more thing that I wanted to mention before moving to the searching in this fan out on request. Okay, that is something, let's say I have to write it down. Let's say someone is searching Java and someone is searching Java. Okay, and there are some posts exist related to JVA as well. So let's say if I say there are, let's say, 10 posts. Okay, and for Java, let's say there are 1 million posts. Okay, this thing will also an important point to consider. That's why we are doing it before the ranking. So let's say someone is searching JVA. Okay, there are 10 posts, and in Java there are 1 million posts. Now the thing is, let's say if a user come and make a request for JVA, okay, and we have to return 20 results. So in the search service, there is a point of query expansion. So what is going to happen in this query expansion? In Elasticsearch supports fuzzy searching. But here there is a search service. What the search service will do? It will do some cosine similarity. It will do some vector embeddings. It will figure it out the nearest word related to JVA. Okay, so basically with the JVA, the nearest word is going to be Java, okay, Javas, okay. So there are going to be related word related to, there's going to be a word related to JVA. So when this fan out request will going to come, it is not only going to come with the JVA, it is going to come with the Java, Javas, okay, and there are any other words related to this concept, okay. So it will going to send you multiple requests because it's a fan out request and it can be come on many topics. That's why we are using this fan out request, and that is the purpose of this query expansion and spelling similarity and the cosine similarity that I was telling you. That is why we have this search service. Now we didn't discuss about ranking anything. Now when we send this request, it is going to give you some results, and then when the results go back to the search service, okay, then there's going to be ranking, okay. That ranking is going to be, of course, JVA post that we get from the JVA should be more prioritized because that is the actual request. Java is going to be less prioritized because there is going to be some difference from JVA. Java's posts are going to be less similar to JVA, so that they are going to be deprioritized. This is the whole thing that I wanted to tell. Now we are going to discuss about the actual ranking. So I think I made you explain this, how JVA, if how the fuzzy search is working here, how the similarity is working in our Twitter. Now let's talk about the ranking. So basically we have discussed these three things: static, dynamic signals, and the query time. What is going to happen if we go and do this sharding? So basically there is going to be a service that we haven't discussed, is the backfill and the engagement service. Think of it, there is a tweet and it is going to get so many likes again and again. So we are not going to come to the database, to this distributed Leucine index, and update it. Once in a while, let's say once in a day, we will come and we will update that particular tweet with, let's say, 5,000 likes and all, and that we will just do a bulk update. Similarly, we will do the bulk updates here. So that is the backfill service and the engagement service that this service will do. And once we change this, now we are going to work on the ranking algorithms. So now we figure it out that these dynamic signals, query times, and static signals are responsible for our ranking. So I told you this searcher will search on the segments, it will get some data, and after that we are not going to return 100 records from this particular shard. What we are going to do, this searcher will also do some ranking. What is this going to be ranking? So basically it is going to rank on the basis of the dynamic signals. Okay, so now they're going to be the custom code. Which person has the most likes? It is going to be based on the retweets, or basically they can put some ML algorithm also here. They can directly call the machine learning algorithms and figure it out. Out of these 20 posts, which out of these 100 posts, which are the top 10 most important posts for that particular user. So they can put any machine learning algorithm, they can write some custom code here. So this is how this ranker is going to work. And this ranker is going to be present inside this. And this ranker is going to be present inside this Earlybird distributed Leucine index. Now there is one more thing that I wanted to tell. Let's say if from this shard 1, let's say we get good 10 posts. Of course, they are going to be ranked. From this shard 2 also we get 10 posts. This shard 3, 10 posts. And again, from so many shards, we get 10 posts. When this fan out of request is come, we get these 10 posts, we send the response. Of course, the responses are going to come from many services. Let's say there are 10 shards running, then we are going to get 10 responses. So it means that we got 100 tweets. Out of these 100 tweets, now what we should do? We should again response it back. We should give it back to the user. But out of these 100 posts, which 20 posts we should send? Like, what are the top 20 posts? Then in that case, what we are going to do, we are going to do a re-ranking. That's why I mentioned a re-ranker. So again, there is going to be a re-ranker exist in the search service that will re-rank. Out of 100 posts, it will re-rank it and then it will send to the user. So that is how the user will get the very good 10 posts, 20 posts, very good 20 posts. Now, as I told you that we are going to get 100 posts from our Leucine index, but we send 20 and now the 80 are still left. The next time the request will come to the search service, we'll just going to call the Redis, and this Redis has some TTL for these 100 tweets. Let's say next 5 minutes, we can respond it back with the help of this Redis, and after that this request will die. And then again, we will make the query to the Lucene index, and then we can respond it back again. And this is how the searching is going to work in Twitter. And this is very similar to Elasticsearch. And this blog I'll provide you on my website. You can just go and check it out. So this is it for the video, and I hope you will like it. And thank you for watching me, and we will meet in our next video, and bye bye.